Hey, so hello there and welcome back. And in this video, we are going to talk about a special type of tree, and that is the binary search tree, often abbreviated as BST. So before we start with anything, it is important to understand what are the special conditions that makes a tree a binary search tree. So the criteria that a tree must satisfy for it to become a binary search tree is that for every parent node, the left child should contain a smaller value than the parent node, and the right child should be in value greater than the parent child. So what we are saying is, if this is the parent node and also the root of a tree, the child value is lower than the parent value, that is 5 is smaller than 7, and the right child is greater than the parent value, that is 7. So parent is greater than 9. Again, if we talk about the 5 as a parent, the left child is smaller than 5, that is parent, and 6, that is right child, is greater than the parent. And similarly for 9, this node, the left child is smaller, that is 8 is smaller than 9, 12 is greater than 9, that is right child is greater than the parent child. So if every node satisfies this condition, every node having a child satisfies the condition that left child is smaller and the right child is greater in value as compared to the parent, we can say that the tree is a binary search tree. Now I have marked a good binary search tree and bad binary search tree, and we'll come to that later. First of all, let's understand what is the advantage we are getting from this binary search tree. So if you have practiced and explored enough about the arrays, there is binary search, and the algorithm of binary search, the advantage that binary search algorithm applied on arrays gives us is that we can search any element in an array in O of log n. So that is the benefit we also get in the binary search tree, that we can get an element in O of uh, not n but log n time, and which is relatively much faster than O of n. But the additional advantage that we get in binary search tree is we can not just search an element in O of n time, but we can in fact insert elements in just O of log n time on an average, and we can also delete elements from the binary tree data structure in O of log n average time. And it is not the worst time, but the average time, the reason is that it depends on the tree that we are dealing with, and there comes into the picture the good tree and a bad tree. So if a tree is good, the time complexity will be, on the worst cases, will be O of log n for search, insert, and delete. But if the tree is in itself a bad one, the time complexity can go as down as O of n. And how does that? What I mean is, you see that in this tree it is quite height balanced. What I mean by height balanced is the difference between the leaf nodes is 0. But over here, the difference between the leaf nodes is not 0, but in fact, it is a gap 1. And you can see that there is a very linear kind of chain being built here. So this is nothing but, if I see that, it is just an array form of data structure being built, and it will limit us in the insertion and deletion. So the idea is to keep the tree balanced in height, because if the tree were to go on like in a linear fashion, right, like this in the downwards direction, only in the right child direction, what will happen is eventually we will build an array, a linear data structure, and it will not give us the flexibility or the power to insert and delete elements in O of log n time complexity. So the idea is that do not choose your root 7, but choose some root over here. And when you choose the root over here, the tree will be much nicer, or at least nicer than this, and the structure will be more height balanced and mm, uh, And it will just be helpful for insertion and deletion with efficient time complexity. So that is what I mean by a bad tree and a good tree. So before we move on to our editor and do the coding for binary search tree over there, I want to just recap what we learned. Binary search tree is a special tree where the parent node has a value greater than the left child but smaller than the right child. And this is true for all the nodes on the binary search tree. The advantage or the need for this data structure comes from its ability of insertion and deletion of new values to the data structure in just O of log n time complexity. And remember, O of log n is much faster than O of n. So there are good binary search trees and bad binary search trees. And to identify them, the difference is that a good binary search tree is height balanced. On the other hand, the bad binary search tree is not height balanced. It looks more of a linear data structure, and the time complexity for insertion and deletion, and in fact, search can go in worst cases as bad as O of n, which is pretty bad. But on the other hand, for good binary search tree, the worst time complexity is as good as O of just log n. So these are the three things that we learned about binary search trees. And next on, we will be moving on to our editor where we will code the data structure. So here we are on our editor, and here I have defined a class node that contains essentially a value and left child and right child references. So now I'm going to create a class by the name binary search tree, and I'm going to define functions that will perform the binary search operations of insertion and finding the value for now. We'll skip the function for removing the node for now because our objective is to just understand the basic flow or the logic that goes behind building this data structure. So for initializing the class, what I will do pass is just that the root of this binary search tree is nothing, it's none. So this is the constructor for this class. Now this class will consist of two functions, as I mentioned. One of the function will be insert, and its functionality will be to insert the value or insert the node to our binary tree in the binary search tree fashion. So it will take a value, create a node, and add it to the appropriate place in our binary search tree. Other function will be the find function that will take a value from the user and find it on the binary search tree and return the output as if it has found it, then it will return the node, and if it fails, it can say that whatever you're trying to find is not on the tree. So now let's start by coding the insert function where we will apply the logics to ensure that the new nodes are added in the binary search tree in the appropriate places following the conditions, that is left child is smaller than the parent and right child is greater than the parent. So first of all, I'll create a new node, and to do that I will make a call to the node class. And when I do that, the initialization or the construction function will be called, and therefore I will be able to create a node object, and that object will be referenced by the variable new node, and this object has three properties. So it has a value, and it will be the value that that the user has passed to the insert function because I am passing it to the node class initialization as well. And for now, its left child and right child will be set to none. So enough with the over explanation, and let's move fast. So base condition is if there is no root to this tree, what we will do is we will make this new node as the root of this binary search tree. So if there is no root and you are inserting a node, it will become the root of the tree. Now, if that is not the case, what we will do is we will define a current variable which will point to the root of the tree, and we will now starting from the root do perform the binary search operation. So using a loop, I will traverse the tree and find the perfect spot to fit this value. So first of all, if the value is equal to current.val, I want to just stop everything because we are assuming that our binary search tree does not contain multiple instances of the same value. So if the value is same as a value on the tree, we are not going to do any insertion operation at all. Other than that, if the value is less than the current.val, I want to go to the left child because then I can repeat this loop over and over until I find the perfect spot. So to do that, if the value is less than current.val, what I will do is if current.left equal to none, that is there is no left child, then this is the perfect spot. I want the new node to fit here because there is no left child and the value is less than the parent, so it satisfies the binary search tree conditions and I want to fit my new node there. So I did that. But if there is a if there is a left child, what I want to do is I want to traverse it using my current pointer. So I will make my current point to the current dot left child. Now, the other case could have been if the value is greater than current.val. So if the value is greater than the current node, I want to check the right child and perform the same operations that I did on the left child on the right child. That is, check if there is a right child. If there is not a right child, I want to fit my new node right there because it satisfies the binary search tree conditions perfectly and just return. But if that is not the case, that is, there is a right child, I want to traverse it using the current pointer. That is, now my current value becomes current dot right, and I will iterate over and in the while loop, I will just follow along until and unless I find a perfect spot where there is no left or right child and my new node fits. So that is the idea, and we are done with this function. Now finding a value on the binary search tree is very similar to inserting new values, but it is less complex because we just have to check if there is a value existing on the tree or not. So we have to follow the if less than, go to the left child, if greater, go to the right child, which will give us O of log n complexity, time complexity. And we just have to return if we found the value. And if not, we have to just say that we didn't find any value on the tree. So found is set to false. That is, we will set it true when we find the value on the tree that the user has inserted on the find function. So this loop will go on while there is a current pointer not set to none, and found is set to false. The moment we find it or the current gets exhausted, we will get out of the loop. And we will do the typical binary search operation, that is, if value is less than current.val, go to the left child, that is current becomes current.left. If the value is greater than current.val, go to the right child, that is current becomes current.right, and this will again happen in a loop, while loop. So the current is just getting updated and will go on. But if the value is not less than current.val and not greater than current.val, else, that is, the value is the only remaining case is equal to the current.val, we set the found is equal to true, and that will trigger the while loop to break out of it, and we will be outside. And if not found, we want to return there is not in tree, which says the value is not in tree, it actually means. So we can just say not in tree. Other than that, if that is not the case, if found is set to true, I want to just return the current, and current will be pointing to the node with that value on the binary search tree. So with this, we have a concrete, crystal clear understanding of the binary search tree. We understand what it is, what are the advantages, and then we actually coded the logics on our editor, where we understood how to code the logic or what are the logics that goes behind the binary search tree optimal insertion and finding operations that take O of log n time. So that is it for binary search tree.